talking about characterizing functional connectivity, subnetwork contributions, and narrative classification with Shapley values, which is an impressively long time. So go ahead and start, Leslie.
Okay, yeah, thank you everyone for coming. Today I'm going to talk about permutations, but I will also introduce my research group a little bit first and what we are working on. So the name of my research group is Geometry and Machine Learning, and we're basically working in two areas that are a bit different but also connected. And the first big topic is really about how do you generate geometry and how do you analyze it. So this is a lot of the things that you do in computer graphics and computer vision. 3D reconstruction, how do you find out if you have 3D shapes, which are the same parts, which are different, and how can you analyze, okay, what is a good representation for geometry? Because this is actually quite a complicated problem and it really depends on what you want to do, what works well. And then the second part is how can you use geometric ideas to improve machine learning itself? So this is related in the sense that we do geometric optimization again, and we use a lot of the ideas that you can also use in 3D data, but we want to apply it directly to machine learning. So for example, you can say here, if you have autoencoders, or actually in general, if you have any neural network, you have all these layers, and in between you get some kind of representation that's called the latent space, and then you can use geometric optimization directly on this representation. And then the same as in just 3D data, it depends a lot how this representation looks like, what kind of optimization works well. And actually, so the talk I'm going to give today is about the second talk, and it's about, okay, if you have permutations, how should you represent them in neural networks? Because permutations are really hard to optimize. But just to give you an idea about the first part, so 3D reconstruction is probably a problem that you're all aware of. So you're given a bunch of images, which are 2D, and then you want to find out, okay, what's actually the 3D geometry that is actually represented, that's depicted in the images. And then you have a lot of problems with shadows and finding out, okay, what's actually a shadow, what's part of the texture, how does the actual geometry look like? So this is in general a pretty ill-posed problem. And then the question is, okay, how can you really get the true geometry and also in a very high resolution way? And for that, there's actually a bunch of different representations that you can represent your geometry in. And depending on what you do, some of them are good and some of them are bad. For example, there's signed distance function, which is basically a field in your whole embedding space, and then you want to represent the surface of your geometry. And then the signed distance function basically gives you, okay, what's the distance at each point to the surface? And this is pretty good if you're doing optimization in neural networks. So this is something that neural networks can represent well. But it's also a bit complicated if you want to look at the surface, because the surface is not like explicitly given. You cannot say, okay, these are a bunch of points on the surface, but you first have to find them by going through the signed distance functions. And then there's, for example, a 3D Gaussian spotting, which is basically just a bunch of Gaussians, so points with some Gaussians attached in 3D space. And they are really, really good for rendering. But then again, if you want to look at the surface, there's no explicit surface information because it's just a bunch of points with some variants attached. So if you want to find out, okay, what's actually the geometry that you're representing in the scene, it's again not so obvious. And the very classical way to represent geometry is actually triangular meshes. So you just have points and they are connected by triangles. And there it's very explicitly modeled where's the surface of your geometry. But this is very hard to optimize because triangles are like discrete objects, and optimizing them, getting them out of the neural network is actually quite hard. So what's the best way to do? Like, there's no best way in general. It really depends on your application and what you're doing afterwards, what you should choose. And this is one part of the research that we do. And then something completely different, but that also depends on the representation and is also geometry optimization, is this kind of, well, I call it stellarator optimization. So stellarators are a type of plasma fusion reactor. And first you mentioned, okay, what's the geometry part here? So what happens in the plasma fusion is that it goes around in this kind of torus shape. And then there are these magnetic coils here, and they determine how the plasma flow looks like. And depending on the shape of the plasma flow, it basically, okay, how efficient is your fusion? How do you have to build these magnetic coils? How sensitive is it to little errors in your magnetic field? So this is really important. And then the question is for this plasma flow, okay, it's kind of a torus, but you have to twist it. And then depending on how you twist it, you get different properties. And the question is, okay, what kind of twist is like the optimal one that you should apply in order to get a good fusion efficiency, but also in order to be able to build the magnetic coils, etc. And in order to make a machine learning problem out of it, the question is, how do you represent this for machine learning? And the problem is kind of that the way that the physicists have been representing basically this deformation of the torus is in this kind of Fourier basis. So this is just an example of one of the basis functions related to Fourier analysis. So if you know spherical harmonics, so this is exactly the same thing, just on the torus. And this Fourier basis is very good at representing smooth functions. And the reason why they're using this representation is that all the simulations that they do, they take this as input. So it makes sense for them to do that. But then on the other hand, the problem with the Fourier basis is that they are not local, right? So all the Fourier bases, they are localizing mostly everywhere on the torus. So if you change one coefficient in the basis, everything will change a little bit. And then if you do machine learning, it's kind of hard for the algorithm to predict what happens if I do a little change in the coefficients, because the shape can actually change quite a lot. So part of this research project that we are doing is how can we convert this in a representation that's well suited for machine learning, but at the same time can be converted back into this representation, because this is what we need to do the simulations. Yes, so this is an ongoing project. And this is actually very like, the simulations are very sensitive to little changes in the geometry, so it actually has to be quite accurate. And then from the second part of types of research that we do is this is just general latent space analysis. And this is really just, okay, can we use geometric optimization in the latent space? And there's something called Platonic representation hypothesis. And it basically says, okay, actually neural networks that are trained on different objectives and different data are still, like if there's a lot of data, are converging to the same internal representation to a certain degree. And then the question is, can you actually make use of this knowledge in order to design good neural networks that find these representations, to prove properties of the neural networks, like how the output exactly look like, to improve convergence and reuse the networks that you have. And this is a big area of research. And we're going to look at one aspect of this now, and this is how you can represent permutation matrices in neural networks such that they can be optimized well. So permutations are just bijective mappings from a set to itself. So it's just you take a set and then you assign a new element of the set to it, and it's just exactly one for each object. And implicitly, permutations show up in a lot of different applications. So if, for example, in cryptography, if you have different kind of ciphers, you're just replacing letters with each other that can be represented by permutations. Then also often you have group structures where you're moving things around or transforming them, and you can show, okay, this is actually equivalent to the group of permutations, and then you can use this knowledge to show certain properties. And then maybe more the direction that we will be looking at today is like data structures. So very often you have sets, but then if you put them in the data structure, you will probably just store them in an array, because that's the most efficient way that you can do that. And then you kind of have a set that doesn't have an explicit ordering, but after you put it in the array, it does have an explicit ordering. And this can be kind of a problem if you want to have applications that do not depend on this ordering. So for example, what we're looking, or what we will later see as the application is you have the 3D mesh, and then maybe you have a similar 3D mesh, and you want to find the points that correspond in these two meshes. And then you might want to represent this as a permutation. So you want to find this actual permutation. And to do that, you have to represent the permutation somehow. So before I just said, okay, it's a bijective mapping, but if you put it into your computer, you have to represent it somehow. And one way to do this is just the same as in the array. You just number all your elements, and then you say, okay, I have a new vector, and it just assigns the number to where the element is supposed to go. So this is pretty easy to do, but it's also kind of a complicated way to represent this, because now you have a vector and every number can only show up once. And if you're supposed to check if a vector has this property, it's actually not so easy. So it's not like computing the norm or something. So actually have to count all the elements and check if there's just one of them. So this is something that's really, really hard to optimize in any kind of optimization framework. And also okay, I'm gonna go back. So the other thing that's really hard is interpolate between different permutations in this representation. And the reason is, so if you look at neural networks, the setting is normally, okay, we have some kind of function that the neural network represents, and it's parameterized by some weights that we call theta. And then we have some training set. And when we update the parameters, what we do is we have some kind of parameters. We compute the loss based on the training data that we have, and then we update the weights. So here we have our previous parameters. We know, okay, we should go into this direction. This will be our correct new parameters, but because the gradient is just a linear approximation, probably not going the entire way, but we do like the small step size updates and gradient descent. And of course, so here, if you don't go the whole way, it's kind of an interpolation problem. So if your data doesn't interpolate well, that's a big problem. And you might have seen exactly the same thing if you ever did the classification problem. So if you have image classification and you want to know, okay, what kind of animal do you see in the image? So here we have the options owl, rabbit, cat, and squirrel. Normally what you don't do is say, okay, your network should output the word rabbit, because neural networks are not very good at that. Instead, what you do is you just assign numbers to each class, and then the network is supposed to output the number, because that's much easier. But then in this kind of gradient descent setting, this is actually not a very good representation. So let's say we have our neural network and we're seeing this image and it's saying, okay, 0, that's an owl. And we can see in our training data that it's wrong. So we compute the gradient and say, oh no, update the parameter so it says cat. But then we just do like half an update step. So let's say this would lead to just our output being interpolated in the middle, and then would output 1. But 1 would mean, oh, okay, now it's a rabbit. And this is kind of really bad behavior, because neither our network nor our training data said anything about a rabbit. So this is really unpredictable, really just depends on how you assign these values. So this is quite bad. And even worse is, so maybe you don't exactly land on the 1, but you get like 0.7, and 0.7 doesn't mean anything. Like this was not one of the options that we said were corresponding to classes. And so again, just having these integer values for the classes is pretty bad. And this is also why almost never, if you do classification, you do it like this. But what people normally do is you have like this whole vector of values as the output, and each element of the vectors represents one class. And then the higher the output, let's say, the more likely. So you could say this is a probability distribution, which is very often not the case, but you just say, okay, it kind of corresponds to how much the network think this class is the output. And now if we look at the previous example with gradient descent again, the great thing is okay, we were first predicting the owl, but we wanted to predict the cat. Now when we interpolate, what we get is a vector that is like half-half between the two of them. And this is both related to what the training data told us, and it's also like a valid representation. So this works much, much better if you train a neural network. And we can do basically the same thing also for permutations. So before and here, now we had the single value for the class and we kind of lifted it to the whole vector. And now for the permutation, we had the vector. So we're going to lift it to a matrix. So there's a set of permutation matrices and it's defined by like this. So it's just a quadratic matrix with these properties, and what they lead to is, so it's all zeros, but every row and every column has exactly 1, 1. And then if you multiply a vector with a permutation matrix, we'll just reshuffle your entries. And just as a property that I will use later on, so all permutation matrices are full rank, which is pretty easy to see because you have to check if all the columns are orthogonal to each other, and because they only have 1, 1 entry, they are all orthogonal. And then there's the bistochastic relaxation of permutations, which is just values between 0 and 1, and they should all sum up to 1 in each row and column, so you can do this kind of interpolation. So this is pretty good, but the problem here is still, okay, this is a quadratic matrix, so normally you would not want to optimize over a quadratic matrix. And the other problem is if you do this relaxation, you normally don't end up with a permutation. So these permutation constraints are super, super hard. So if you have here 2 different kind of problems where you're optimizing over the set of permutations. So the one has a linear optimization function and the other one has a quadratic one. And normally you would say, okay, linear and quadratic functions, they're pretty easy to optimize. But just because you're optimizing over the set of permutations, which has like this very complicated constraints, you can see here, okay, so the linear assignment problem is still solvable in polynomial time, but the quadratic assignment problem is actually NP hard. So this is really, really hard. And if you just replace here the permutations with bistochastic matrices, you're normally not going to end up with something that's similar to a permutation anymore, which might be a big problem for your application. And now the question is, okay, what can we do about it? So we both want to find permutation, but we also don't want to optimize a quadratic matrix because it's very expensive. And the question is, can we kind of decompose our matrix into 2 other matrices? So this is a very common approach if you want to optimize matrices in an easier way. And then the question is, okay, we want to decompose this in 2 smaller matrices. And we hope we don't have to optimize as many parameters. So we're looking for some matrices V and W that are only n times k, and we hope that k can be much smaller than n. And then the first question for you is, do you think that's possible to find matrices V and W like this, so that we get a permutation? So I'm gonna spoil the answer. The answer is no, but do you have an idea maybe why it's not possible? So the problem here is, so I said before, permutations are always full rank. And if you have 2 V and W matrices that only have a dimension k in one direction, then they can have at least 1 k. And if you multiply 2 matrices, they will always inherit the smaller rank. So just by this property, it's not possible that this linear multiplication of the 2 matrices can be a permutation. But, so this only holds for normal matrix multiplication because it's linear. We might be able to do a nonlinear decomposition. And nonlinear in this case just means we will put like a nonlinear activation function that you know from neural networks around this V and W. And the first thing that I will convince you of is that in that case, for any permutation, you can do it with k equals 2. So these are really, really small matrices. Well, the other one is still n, but k equals 2 is pretty good. Yes, so this is what's standing there. Any n times n permutation matrix can be decomposed in the product of two n times 2 matrices in this form, where sigma is just some kind of nonlinearity. And the construction is actually pretty simple. So let's say that in our n times 2 matrices, every row is just a 2D coordinate. And all the 2D coordinates, they're not even arbitrary, they're all lying on this unit circle. And then for this example, we're also saying V and W are exactly the same. So here you have the blue point, these are the blue coordinates, and these are the same. And then we just do the matrix multiplication. And because they're on the unit circle, if they're the same point, it will result in 1. And if they're not the same point, it will be something smaller than 1. So now we can do our nonlinearity, which in this case is just thresholding at 1. And in this case, you get the identity matrix. And this is one permutation. And then I hope you can see that if you would reshuffle the columns here in a way that any permutation matrix might do, you would also reshuffle the columns here, and you could generate any permutation matrix that exists. Okay, so I mean, this is pretty cool, but you can see here, okay, I mean, this is an example for 4 points. Now I said this works for any n could also be 1 million, right? And in that case, at some point, you will probably run into some numerical errors, because when points are too close to each other and you threshold at 1, there might still be some kind of issues. So something that's kind of necessary is that the points are not too close to each other. So just like this, so if you have the points, they should be distributed as equally as possible on this unit circle. And then if you do the same multiplication, I mean, it's still the identity here in the middle, but the other values, they are further away from the 1, which is good. But still, for 1 million points, probably there would still be numerical issues. So what we now need is a little bit more space on our unit sphere. And what would be a way to get a little bit more space?
Could we allow the interior of the circle also to be used, or am I misunderstanding this?
We could do that, but it would probably lead to problems, because then we wouldn't know anymore if the inner product is 1, because it would be a lot smaller. But what we could do is we could increase the dimension of the unit circle. So we could just take the unit sphere of higher dimension, and then we have a little bit more space. But of course, we don't just want to have an arbitrary dimension, because the dimension of the units circle or sphere that we're taking is kind of this k that we had before. So if we just take 1 million for the dimension, then we haven't actually won anything. So the question that we need to answer kind of is, okay, what's a good relationship between the n and the k? So how can we take n points such that we can guarantee certain behavior when we distribute them on a unit sphere of a certain dimension? And there's something called the Kissing number that answers exactly this question. So the Kissing number is the greatest number of non-overlapping unit spheres that can be arranged in space such that they each touch a common unit sphere for dimension k. Okay, what does it mean? We just say, okay, we have some kind of unit sphere in the middle. So in dimension 1, it's just these 2 points. How many other unit sphere can touch it? And in dimension 2, because 1, because they're just 2 points, it's just 2. And then you can see here, okay, in dimension 2, you can arrange 6 circles around it. And in dimension 3, you can arrange 12 unit balls around it. And here you can already kind of see that this is not a super obvious problem, because you can see that it's not tightly packed anymore. So there's a little gap. And the answer is actually not so easy when you go to higher dimension, but you can still approximate it. So now does someone want to guess what's the Kissing number for dimension 24. So how far does this grow? Just
36.
36. Okay, that was the guess. So the number is 196,560. So this.
Second one.
Yes. So this number grows really, really quickly. And you can see here what's kind of interesting, like the exact number is actually not known for a lot of dimensions. But for some reason, for 24, it's known. And this is actually a quite recent result. So in 2022, there was a Fields medal for this result. And also because the proof was very, very elegant. It's actually much shorter than for dimension 3. But I don't know why. Okay, so, but to come back to our permutation problem. So what's happening here is exactly this column is going to be the K, and this problem is going to be, or something in between here is going to be the N. So if we have, I don't know, roughly 200,000 times 200,000 permutation matrix, we can represent them on the unit sphere of dimension 24, which is still pretty small matrices in comparison to this whole quadratic one. Yes, so this is basically just what the formula said. So we changed the formula a little bit for the proof, and the nonlinearity is then a ReLU function just because it's easier to prove them, but you can just imagine that it's thresholding at 0.5, and this corresponds exactly to 60 degrees difference between all the points. So you can show, okay, if you have this property, then for the Kissing number, and you arrange them in the correct dimension, then you always have 60 degrees difference between all your points, which is quite a big gap. So this is quite stable. But then, of course, in reality, maybe you might even choose your numbers a little bit bigger to give your optimization a few more degrees of freedom. And this is cool. So you can represent all your permutation matrices like this. The problem is, of course, not every V and W is going to give you a valid permutation matrix, right? If you do it like this, you can still end up with V's and W's where, I don't know, your points are too close together, and then it's not a permutation anymore. So the question is, if we use this in optimization, does it still work? So we did some experiments with the quadratic assignment problem. So this is the same problem from before, that was NP-hard. And we just implemented the gradient descent to optimize the quadratic assignment problem. This in general is not a good way to do it because NP-hard problems and gradient descent don't go well together. But this is mostly to show that if we do the optimization, we will get permutations out. But of course, if you just do the pure optimization on this loss function, you will not get a permutation because this loss function doesn't know anything about the permutation properties. So you have to add like some kind of regularizer that says, okay, the result is supposed to be a permutation and it's supposed to have this kind of properties. And these are the results. So there's some data set with reasonably complicated quadratic assignment problems. And you can see here, so this is the size of the instance, which only goes to 150, which is not even super big. And this is the error that we got. And you can see, okay, it's not always the optimum, but very often it's close to the optimum, which is nice because we put a gradient descent on NP-hard problem. Much more interesting is that how many of these outputs were actually permutations, because this is what we actually wanted to check. And it was 75 out of 87, which is not all of them, but nearly all of them. And also all of them that are not permutation, they're actually always just 2 columns where this is where there's a double 1 and one where it's all 0. So it's very close to a permutation most of the time. But the problem you can see here is that with growing instance size, actually the runtime also goes up very, very quickly. And the reason is, well, we had this nice representation. But when you look at this formula, you still have to compute the whole matrix. This is just, I mean, optimizing over less parameters, But then when you calculate the gradient, you're still computing the whole quadratic matrix. And this is just not good. So you get very high memory requirements and also very slow runtime. So you didn't actually win anything yet. But this was more of a proof of concept. We also put this into a real learning pipeline. So here we have the problem that that I told you about before. So we have two 3D meshes, and you have the points, and you want to find out, okay, which of the points are kind of semantically related to each other. So the output here is a permutation. And so we used an existing pipeline that outputs a permutation, or they're actually outputting like a bistochastic matrix. And we just put in our formulation for the permutations instead, and then checked, okay, does it still work well? And you can show if you just use the representation, the results don't really change. But the fun thing is that if you look at the loss function, you actually don't have to look at every entry in the matrix at the same time, because it's like an element-wise formula. So you can do just inner product of some row and column, and then the element-wise nonlinearity, you can just choose like randomly or not so randomly a few of the entries and only use those for the loss. And then you get rid of your memory problems. So this is what this parameter k says. It basically, okay, let's say what percentage of the matrix do we actually evaluate in the end? And then you can see here full is the original pipeline or computing the whole matrix. And then if you have a smaller k, then the memory requirements go down a lot. And you can also see that, of course, okay, if you just use very few entries, then your results are not so good, but actually pretty quickly with higher k, you get pretty stable results that are comparable to what happens if you have the full matrix. Yes, that was it. So just to sum up the results here, choosing a good representation actually has a huge influence on what kind of results you can get. Permutations are very complicated, and if you just try to optimize them, you will probably have a hard time. And there's actually another solution that you can do. So in many problems, you actually have like this kind of implicit dependency on the permutation. So you don't actually want to compute the whole permutation matrix, but you want to be independent on what your permutation is, for example, the ordering of your vertices. So in that case, you can actually build permutation invariant networks. So you just cancel out the whole permutation thing. And this is something that you can hear about in my lecture that's called geometric deep learning. So if you're interested in that, so I think for this semester it's so late, but it's going to happen next semester again. Okay, and with that, I will just leave you a few teaser figures for thesis topics on 3D reconstructions that you can do in my group. And otherwise, I'm happy to take questions.